Okay, so we've used matrices to solve systems of linear equations. We've done some work with, what do you call it, simplex method in using this to solve an optimization problem. Now we're going to kind of get into some of the matrix arithmetic and algebra here. So we need to establish some ideas. Let's establish what it means for two matrices to be equal. So this is the equality of matrices. Alright, so this is pretty straightforward. If I have two matrices A, which is given by aij's, so all the elements are aij's, and B, where all the elements are bij's, ij, and these are both matrices of the same size, m by n, and if aij is equal to bij for all I up to m and all j up to n, then we say that A is equal to B. So we say that the two matrices are equal if all of their elements are equal. Okay, so that's pretty straightforward. Let's get into matrix addition. Matrix addition is very similar to vector addition. If I have two matrices, A, where all the elements are aij's, and B, where all the elements are bij's, and these are two matrices of the same size, m by n, then A plus B is equal to the single matrix where I take all of the aij components and add them to all of the bij components. So matrix addition is done component-wise. You just add up all the corresponding components and you get a new matrix of the same size. Okay, so we can also do scalar multiplication. This is again very similar. I'm going to have A being a matrix with aij's, and it is an m by n matrix. I'm going to be given some little c, which is a real number. Then c scaling A means that I get the same size matrix, but I just take c and multiply it by all the aij's. So if I scale all the components, I have scaled the matrix. Okay, so this is where things get a little bit weird. So if we do matrix to matrix multiplication, so we're going to call this matrix multiplication. Okay, so here's what happens here. I am going to let A be the matrix all the aij's. And this one has to be m by n. B is going to be all of the bij's, but this one has to be n by p. And then I am going to let AB is going to be an m by p matrix. So I'm going to take the m from here, the p from there, such that AB is this like mixture of Cij's, where each Cij is equal to the sum from k equals 1 to m, right? K equals 1 to m. And take that back, it's k equals 1 to n. That should be an n up there. N of the aik's times the bkj's. j's. Okay, so this is kind of an interesting reality, right? We're basically taking a dot product here. We're taking a dot product of the ith row of the A matrix and the jth column of the B matrix. So the ij element of the AB matrix is the dot product of the ith row of the A matrix with the jth column of the B matrix. So let's take a look at what this looks like in reality. Okay, so let's take two matrices for example. So let's take A, which is -1, 3, 4, -2, 5, 0, and we're going to multiply this by B, which is -3, 2, -4, 1. Okay, so this is a 3 by 2 matrix. This is a 2 by 2 matrix. So AB should be a resulting 3 by 2 matrix. Okay, so what we do is we take the first row of A and dot that with the first column of B. So this is going to give me -1 times 3 is 3, and 3 times -4 is -12. Okay, so now we take first row of A, dot that with the second column of B. So this is going to be -2 plus 3. See, second row, first column. So this is -12 plus 8. Second row, second column gives me 8 minus 2, right? 8 minus 2. Third row, first column is -15 plus 0. Third row, second column is 10 plus 0. So the resulting matrix should be 3 minus 12 is -9. -2 plus 3 is 1. -12 plus 8 is -4. 8 minus 2 is 6. -15 and 10. So this is the appropriate 3 by 2 matrix that I end up with. Okay, so this is a little complicated. You might want to practice some of these by hand. MATLAB does this automatically for you. You just punch in the two matrices and multiply them, and this is exactly what it knows how to do. So I want to note something. AB does not equal BA. This is really, really important. There is no commutative property of multiplication here. It wouldn't even work. You can't multiply these even by dimension going the other way. So we don't get any commutative property. Now there's a lot of reasons for establishing multiplication this way. One of them is going to be the idea that composition substitutes for functions in matrices, and we'll get into that. But another one is it's just makes it really easy to find another way to represent systems of equations here. So let me show what that looks like. Okay, so let's start with the system of equations. a11x1 plus a12x2 out to a1n xn is equal to b1, a21 x1 plus a22 x2 plus a2n xn is equal to b2, and then we keep this going and we go to a m1 x1 plus a m2 x2, that should be an x2, plus a mn xn equals bm. Okay, so there's my system of m equations with n variables. Okay, so the first thing we do, I'm going to make this into a matrix. This is actually a simple move. I'm going to play a little game here, and I'm going to kind of It's not going to work. Yeah, I'm going to kind of hack out the end of this a little bit and rewrite a little to make something work here. So, oops. Let's try that one more time. There we go. And we'll delete that. And then we'll kind of repair it a little bit. Right, so what do we have here? We have to turn that off. There we go. So this was xn. This was amn xn. And I'm going to put just a single x equal sign here and then make this b1, b2, bm. Okay. And if I put a bracket around this and a bracket around that, I now have a m by 1 matrix and another m by 1 matrix. So that makes sense. Right, I can set an m by 1 matrix equal to an m by 1 matrix. But I can decompose this one on the left. I can put all the coefficients into one matrix. Right? And then I can put all the variables into another matrix, x1, x2, down to xn, rather xn. Okay, and then set that equal to this. b1, b2, down to bm. Right? So if I look at this matrix is an m by n matrix times a n by 1, so that matrix multiplication works, returning me an m by 1 matrix. Now, if I look at this and I do this matrix multiplication, I end up with the original matrix that I started with. You can check that and work that out by doing all of the dot products, and it'll work out quite nicely. So what we do is, in our kind of matrix algebra here, is that this matrix here gets called A, this matrix here gets called X, this matrix here gets called B, and I can write this system of equations simply as AX is equal to B. And we're going to find a way to solve that equation for the values for X. Okay, so that's coming not in this lesson, but it's coming up. But if I establish matrix multiplication this way, solving for X here becomes rather simple and pretty useful. So we're going to hang on to that. Alright, so there's some thinking of why we do this multiplication this way. Okay, so just looking at addition and scalar multiplication, we have some properties that we want to look at. So we're going to let A, B, and C all be m by n matrices, and C and D are going to be scalars. Alright, so one thing is that under addition, we do get a commutative property, A plus B is equal to B plus A. We get a couple of associative properties. A plus B plus C is the same as A plus B plus C. And we can do this also with scalars. So the scalar CD times A is the same as C times DA. So there's a couple of associative properties there. If I scale a matrix by 1, I just get that matrix back. That's an additive scalar multiplication identity. We get a couple of distributive properties here. So if I scale A plus B, that's the same as scaling A and scaling B. And if I add two scalars and then multiply that by a matrix, I can distribute those scalars with the matrix. Okay, so none of these are absolutely surprising. You can prove all of these by using like component-wise proofs with m by n matrices. They're not hard ones to prove. Okay, so let's look at some more here. Okay, so we need a logical 0 So 0 is usually the additive identity. So the logical 0 here is to say I have a matrix O m comma n, and it is going to be equal to all of these aij's, and this is an m by n matrix, right? And this is going to be such that aij is just going to equal 0 for all I equaling 1 to m, and all j being equal to 1 to n. All right, so this is just a matrix where every single element is 0, and if that's the case, this is a 0 matrix. Okay, so we get some properties of this thing. If I take some matrix A and multiply this by the 0 matrix, I get back, or add it to the 0 matrix, I get itself back. If I take A and I add negative A to that, I get the 0 matrix. And finally, if I scale A and I get the 0 matrix, then either one of two things are true. Either A is the 0 matrix, right? Or the scalar has to equal 0. So this is like your zero product rule, that if two things multiply to be 0, one of them has to be 0. But in this case, one of them is a matrix, the other one is a scalar. All right. Okay, so we're going to get into some properties for matrix multiplication here. We're going to let A, B, and C be matrices of the appropriate size. This is somewhat arbitrary. It's just they're going to be of the right sizes to make things work for the properties, and C is going to be a scalar. So number 1, the matrix A times the matrix BC is AB times C, so we do get an associative property here. Number 2, we do get distribution on both the left and right hand side. So A times B plus, not B, B plus C is equal to A times B plus A times C on the left. And we also get A plus B times C is the same as AC plus BC on the right. Now remember, I have to establish both of those because I do not have a commutative property. Okay. We also get a distribution of a scalar, kind of an association of a scalar actually. So C times AB is the same as CA times B, which is the same as A times CB. You can only scale one of the matrices, don't scale both, because otherwise you have some issues here. All right, so let's keep going. Okay, so now that we've talked about multiplication, we need a 1, right? So we need what would be the multiplicative identity. Okay, and this is a little bit different. It's not what we would expect. So we need what would serve in the place of the 1. So we're going to let I of a particular size n be equal to this like aij's, and this is going to be an n by n matrix. So this thing has to be squared. It has to be the same dimension in both, same number of columns as rows. Okay, and what's going to happen here is aij will equal 1 when I is equal to j, and aij will equal 0 when I is not equal to j. So essentially what this is that this thing is the matrix with 1 down the diagonal, and oops, let's fix that. Let's make that look right. That's looking goofy. 1 down to the diagonal and zeros everywhere else. So ones on the diagonal, 0 everywhere else gives me an identity matrix. Okay, why is this an identity matrix? Because it gives me the properties that I want. So the properties here are that if A is an M by N matrix, right? Then A times IN, the N by N identity is going to give me back A, or IM times A, the M by M identity gives me back A. So this serves kind of like the 1 in the multiplication. When you multiply it by something, you get itself back. Okay, we're going to put that on pause for a minute, and we will come back to more about why the identity is important, but this is a really important matrix in the game. But we're going to come back to that when we get into the next set of notes that's going to be on inverse matrices. But today we're going to just take a quick turn into what's called the transpose. I'm going to look at that and give an example of it and its properties. Okay, so let's define the transpose of a matrix. Okay, so A, again, is an M by N matrix. Okay, so in the A is going to be the AIJs, right? So all the components are AIJ. Then A transpose is an N by M matrix, where A transpose is all of the AJIs. So A has the AIJs, A transpose is made with the AJIs. So for example, if A is 0, 1, 2, 4, 1, negative 1, then A transpose will be 0, 2, 1. So this column becomes the first row, and the second column becomes the second row, 1, 4, negative 1. So it's basically turning the matrix over. Okay, so it's turning rows into columns. Okay, so we do get some properties of this, so let's figure out what those are. Okay, so the properties of the transpose. First one, if I take the transpose of the transpose, well, if I make rows into columns and then columns into rows, I get the same matrix back. That's pretty intuitive. If I take the transpose of the sum of two matrices, that's equal to the sum of the transposes. Again, pretty intuitive. If I take the transpose of a scaling, that's equal to the scaling of the transpose. Again, not unintuitive, but this is the tricky one. If I take the transpose of a product, I actually have to get the product of the transposes backward. So AB transpose is B transpose, A transpose. This is definitely not intuitive. It's something that you might want to play around with kind of by hand to see why that works. But that is something that you need to commit to memory. All right, so the beginnings of matrix algebra start with three operators: matrix addition, scalar multiplication, and matrix multiplication. Those are like the basics of our arithmetic here. And we've gotten most of the properties that pertain to this. So that's it for today. And next time around, we'll get into how does the inverse matrix work and what does that have to do with like solving systems and things like that. All right, so thank you.